Hello everyone, this is Finnur Pind, the CEO and one of the founders of Treble Technologies. I am really excited to welcome all of you to this webinar event where we are launching Treble's second product, the Treble Software Development Kit, or the SDK. This is something that we here at Treble are quite excited about, something we've been working on for a long time and are really excited to share with the world what we have been doing. So let's dive into it. I have a presentation that I want to go through, and then also some demos where I'll showcase the SDK in action, and then come back to the slides for some roundup, and then we do Q&A in the end. So, introducing the Treble SDK. Here's the agenda for the presentation. I will first briefly introduce the company, Treble Technologies, and then talk about the Treble platform as a whole, which the SDK is a part of, and our proprietary simulation technology, which is sort of the core of our platform. Then move over to talk about the SDK itself, highlight some of its main features and so on, and then move into what is probably the main part of this webinar today, which is just demoing the SDK in action. And we've prepared 3 demos to illustrate some different use cases of the SDK. The first one has to do with data generation, so setting up and running thousands of simulations in complex acoustic environments to generate audio data, which can then be used, for example, to train audio machine learning algorithms. The second use case is virtual prototyping of audio devices, being able to simulate complex audio devices in complex acoustic conditions and assess their performance and use the simulation to design and optimize such devices. And the last demo is showing how the SDK can be integrated into a third-party tool. In this case, we'll integrate it into Rhino Grasshopper and use it to do a parametric study of acoustics. Once this is done, I'll come back to the slides, show a few benchmarks where we compare measurements and simulations and so on to illustrate the power of and the accuracy of the Treble simulation engine. A few words about what lies ahead for the SDK and how the SDK is priced, and then we do Q&A. But I would of course encourage you to shoot in your questions throughout the whole webinar. I believe there's a form here right below the video where you can shoot in your questions, and we will try to address all of them in the end. Okay, the company Treble Technologies was founded in 2020, but actually the roots of the company go back some years prior to that time to academic research. During these years of academic research, we were investigating ways to simulate sound in a more efficient and accurate way. Ended up with a sort of promising prototype, academic prototype, and then since 2020 we've been converting this prototype into a real product and really kind of building it up from there. It was just 2 guys at the very beginning in 2020, but now we're a team of around 35 people, and our expertise is sound simulation, audio data generation, and spatial audio. The mission, of course, to make the world a better sounding place. So here you see the sort of latest group photo. There are a couple of people joined since this was taken, of our fantastic team, the people that have been building the Treble platform. It's around 75% R&D, 25% commercial and admin and so on. A lot of specialists in sound simulation, computational mathematics, acoustics, machine learning, and so on, software engineering. And we happen to be based in Reykjavik, Iceland, out of all places. The weather today in Reykjavik is not great, but not terrible either. It's kind of a gray day, but that's how it sometimes is here in Reykjavik. Okay, but Treble, the platform. So we often speak about it as a platform of virtual sound, meaning it's a piece of software that can do sound simulation on the one hand and sound rendering on the other hand, this notion of listening to the simulation. And the way the platform is built from now on is it's kind of a 3-piece setup. At the core of the platform is our simulation technology, which resides in the cloud. And then we have sort of 2 interfaces to this cloud-based simulation technology. We have a web-based graphic user interface tailored for acoustic design, in particular architectural acoustics, at least for the time being, which we call the Treble Simulation Suite. This has been available on the market since March 1st, 2023. And now introducing a new interface, a programmatic interface to the simulation engine, the Treble SDK. And I will briefly talk about the engine itself, say a few words about the simulation suite, but then obviously spend most of the time showing the new SDK product. key component of our offering is the sort of cloud-based, web-based nature of it. So all simulations take place in the cloud, which brings about a lot of flexibility and scalability. We use the cloud to accelerate simulations on massively parallel computing architectures. We can run thousands of simulations in parallel. We can collaborate with colleagues and so on. And we have placed a massive emphasis on fulfilling the sort of strictest standards when it comes to data security in the cloud as well. Okay, but zooming in on the simulation technology itself, the core engine. So our approach to acoustic simulations is a hybrid approach. So we kind of combine two different methods or approaches of simulating sound into a single approach. And this is using what's called wave-based methods for the low to mid frequencies and geometrical acoustics for high frequencies. Geometrical acoustics is inherently a high frequency approximation, so it's a fair way to model high frequency sound, but it breaks down when we come to lower and mid frequencies because it's hard to model acoustic phenomena like diffraction and phase and interference and so on with geometrical acoustics. Wave-based methods, on the other hand, they inherently capture these complex acoustic phenomena, so it's natural to consider to combine the two. The reason why this hasn't been done so much in practice to date is because the wave-based part has always been so computationally heavy. So one of the research breakthroughs that Treble has done is to develop a wave-based algorithm that is much, much faster than what's been available to date, making it possible to use wave-based simulations for low to mid, well into the mid frequency range in big spaces, and for smaller spaces, wave-based only even. This is our approach to acoustic simulations. A few words about each solver. The wave-based algorithm is using a finite element flavor called the discontinuous Galerkin finite element method, very suited for complex geometries and high parallel efficiency. We're also very proud of our geometrical acoustics solver, which is a state-of-the-art high-frequency modeler, combining phased image source methods and ray radiosity methods. So it's a pressure-based method. It models boundaries and scattering in a very precise and sort of state-of-the-art way as well. And then we have developed methods to combine these two solver results into a single result. That was the core tech in a nutshell. A couple of words about the simulation suite, this graphic user interface tool, which looks something like this. So it's a web-based tool where you can import 3D models from from SketchUp. Right now we have like a live link connection to SketchUp, and soon with other geometry tools as well, and do all kinds of acoustic analysis in a graphic user interface and simulations. The tool is particularly well suited for architectural acoustics, but also sound system design, outdoor sound simulations, and soundscape design. It has very powerful auralization capabilities. And what we're trying to bring to the table with the simulation suite is, first of all, just better accuracy of simulations through our core tech, which in turn reduces risk and sort of increases confidence in acoustics design. Really trying to make the workflow better, less manual labor, less trial and error, live link connections to 3D modeling tools, web-based, cloud-based, collaborative features, etc. And then making auralizations more immersive and interactive and fun than what has been previously possible. Here's Bradley Alexander. He's an acoustic engineer at Bollinger & Grohmann, commenting that the Treble acoustic simulation suite has allowed his team to work much faster than they have done before, and also commenting on the high accuracy of the simulations. So this product, the simulation suite, has been on the market for a few months now and is advancing at a very fast pace, and that's really exciting. But we are here today to talk about Treble's new product, the software development kit. A software development kit by nature can be used for a variety of things. Kind of the sky is the limit, and I'm sure that it'll be used in use cases which we at Treble couldn't even think of, because it's just a programmatic interface to the simulation tech and can be plugged into anything and used for anything people can think of. With that being said, of course, we have some particular use cases in mind which we are emphasizing or sort of building functions around. First one being synthetic audio data generation. as I commented before, this notion of simulating thousands of complex scenarios to generate data to train machine learning. Audio device prototyping and doing advanced acoustic simulations like full bandwidth wave simulations. Integrating this core tech into third-party tools. We'll show Rhino Grasshopper integration. Could also be, for example, a loudspeaker manufacturer wanting to power loudspeaker software tool with precise room acoustic simulations. So you can use the SDK for this and do parametric studies and other things too. There are many different features in the SDK. Here I'm sort of at a very high level summarizing them. I have one slide on each aspect, but I think they will actually become more kind of tangible when we just go to the demos and see them in action. But let's go through them one by one here at the high level first of what this product can do. First, just commenting on the build-up and nature or in the setup of the product. It is a Python-based SDK. So the reason we chose Python is because it's a very popular programming language and it's in particular used a lot by machine learning teams. So the thinking is that the SDK can be very easily integrated into workflows, Python-based workflows, such as machine learning, data generation, training, evaluation, and iterations. Then by having it in the cloud, that's a very key component because then we can run thousands of simulations in parallel, so we can do accurate data generation in short amounts of time. And we've really strived to make the whole thing easy to use and have it well documented as well. Of course, the core is the simulation engine, and sort of by enabling this kind of programmatic interface to that, then we can work with this engine in ways that we can't do as easily through a graphic user interface. And we can run wave-based or geometrical acoustics or hybrid simulations at any scale really and model detailed acoustic phenomena well. We've spent considerable efforts on source modeling, sound source modeling. So here currently we support modeling directional point sources such as loudspeakers and speech. With the tool comes a database of directional point sources that you can use. And we emphasize that we're modeling both in the wave-based part and in the geometrical acoustics part, the directionality. So particularly the kind of challenging low frequency area is well modeled too. Receiver modeling, such as binaural or human listeners, as well as all kinds of multi-channel receiver devices like speakerphones and smart speakers and AR glasses. This is, by the way, an AI-generated image of AR glasses. We've spent considerable effort on developing methods to model these kind of receivers very precisely, so we can capture the spatial characteristics of sound in these devices and how they impact, how the sound field impacts them, and the geometry of the device impacts the sound field, and so on. And this is done through an approach which we call the head or device-related transfer function approach, and I'll demo this later. And we could, by the way, go to really high order ambisonic, up to 16th order ambisonics in our spatial IR generation and post-processing. Okay, then room geometry processing, that's a key component here. We need to set up different scenarios to simulate. The simulation engines handle very well complex room models, such as curved surfaces and fine details and obstructions and things like that. With the SDK comes a very large database of room models, which is also growing fast and will become bigger and bigger. And you can also import your own 3D models into the SDK, and you can programmatically generate and modify rooms. We have some decent functionality for this now, and then more coming soon as well. And I'll also demo some of these things later. Boundary modeling, the acoustic properties of surfaces have a huge impact on the acoustics of rooms, and in Treble surfaces are modeled very precisely by modeling them in terms of the surface impedance and not just energy absorption, meaning that we capture both absorption but also phase response of materials. With the SDK there comes a large database of materials, which is also growing, and ability to import your own materials. We have various post-processing capabilities, such as plotting all kinds of relevant audio style images or plots and do all kinds of audio post-processing like convolution, for example, and computing acoustic parameters and so on. And finally, various auxiliary functionality which aids the workflow and setup, such as visualizing simulation setups, estimating how long of a compute effort is needed for a given simulation setup, things like this. This will also be demoed. So that was a summary of the SDK. Now I think it's just time to move into a few demos and show it in action. The first demo I will be showing, as previously mentioned, has to do with synthetic audio data generation in complex acoustic environments. The second demo will be virtual prototyping of audio devices in rooms. And the third demo will be integrating the SDK into Rhino Grasshopper. And for this last one, we will, just for fun, the room model that we're going to work with here is actually a room model of Treble's offices, which I show a couple of pictures from here. We'll be playing around with this room geometry and analyzing the acoustic conditions. So let's move on to demo number 1, synthetic audio data generation. Okay, here we have the first demo, synthetic audio data generation, or setting up a bulk simulation and running that in the cloud and getting back results to do, for example, audio machine learning training. So what we see here is what's called a Python Jupyter notebook. It's basically a piece of Python code along with some text and images and so on to kind of make the whole thing a bit more readable. And this notebook is set up in 2 parts, or this demo is in 2 parts. First, I'm going to show just how we set up a single simulation, importing a room, defining sound sources, receivers, materials, setting the simulation up, running it, and doing some post-processing on it. Then I will show how this can easily be extended to setting up thousands of rooms or thousands of scenarios and run at scale for data generation purposes. So let's just dive into the first part, the single simulation. The first step I will do is to initialize or import the SDK along with some other Python packages that I will be working with and initialize the SDK. Okay, the SDK, the way it's structured is it's built around projects, so the sort of hierarchy is around projects. A project is basically a container of simulations and setups of simulations. So each simulation will take as input room geometries, materials, sound sources, and receivers. And out of the simulations come results, obviously, which can then be post-processed either directly or with some auxiliary data as a part of the post-processing, such as head or device-related transfer functions or anechoic sound data. So I'm going to go ahead and create a simple project here and then move over to the room geometry setup. As I mentioned in my presentation earlier, we have kind of 3 ways to work with room geometries. First of all, the SDK comes with a very big library of room geometries that can be useful, for example, in data generation purposes. Secondly, we can import our own 3D room models into the SDK and work with them. And third, we can programmatically generate rooms as well, which may be useful again for data generation purposes. So let's start with exploring the room geometry library. I will then also demo programmatic room generation. The geometry import I will show as a part of demo number 3. So I'm going to fetch here all the categories of rooms that we have in the room library, and we will see some different types of rooms: apartments, meeting rooms, offices, restaurants, etc. And there's some different amount of rooms in each category, and we are continuously building and making this database even bigger. Okay, I'm going to fetch all meeting rooms and work further with meeting rooms in this demo. So here I display just the first 10 meeting rooms, for example, the dimensions and the tags that they have. Okay, I can plot the room geometry and it looks something like this. So we see here it's a sort of rather simple meeting room with some interior furnishing, some geometric details like a door, a TV monitor, and some windows and things like that. We also note some points here in the room model, which is kind of metadata that can be useful, for example, for assigning sources and receivers. And we also see some layers here, so that surfaces in the room have been divided on different layers, which is useful for material assignment, for example. Okay, just for fun, I'm also going to demonstrate a few other rooms from different categories in the room geometry database. Here's an example of a restaurant, which looks something like this. Just one example out of many. Apartments, kind of multi-room scenarios. Here we have an example, so we can have apartments in very different sizes and shapes and number of rooms and so on. And lastly, an office example, which looks like this, open plan office. Okay, I'm going to work further with the meeting rooms, and in particular here in part 1 of the demo, I'm going to be simulating this meeting room here. Okay, programmatic room generation. So we can programmatically generate rooms of arbitrary shapes. We basically can put down points on a 2D plan. And these can have any number of points in any positions, and then we can extrude to give it some height as well. So here I randomly create 5 rooms with 4 to 6 corner points and with some random sizes and so on. And then we can visualize one room that was generated. It looks something like this. And just for fun, let's see one other example. This one looks something like this. One of the things that's on our roadmap is to improve or work further with this random or programmatic room generation, being able to furnish them and things like that. I'll come back to that when we talk about the roadmap. Okay, we have decided that we're going to work further with this meeting room geometry, so next step is to insert sound sources. We have some pretty powerful capabilities of modeling sound sources. We can model directional point sources, both in the wave-based and geometrical acoustics algorithm. So modeling the directionality throughout the full spectrum and modeling it kind of accurately at low frequencies. And with the SDK comes a pretty formidable library of sound sources. So we see here speakers from various different manufacturers. This database is also continuously growing, and we're in dialogue with many of the big loudspeaker manufacturers to get even further or more data. We could, for example, plot or select just loudspeakers from Bose. We can display some information like the on-axis frequency response. We can plot the directivity pattern of this source, and we can plot the on-axis frequency response. But here in this meeting room scenario, I'm actually going to work with speech directivity. And the first thing I'm doing here is I'm making a little loop that assigns a speech directivity or sound source with a speech directivity at each of the seats in the meeting room. So using the metadata from the room to place these sound sources. I give them a random orientation, both in azimuth and elevation angle, like this. I'm then also going to place some speech sources just kind of randomly in the room and give them also random orientation as well. So there's a function here that kind of generates points that are invalid positions in the room and use them for placing sound sources there, 2 sources. I'm also going to put some omnidirectional sources into the room at some random positions to mimic noise sources. So we're kind of constructing a realistic sound scene in a meeting room, which can be used then, for example, to train a speakerphone device to pick up voice. Okay, that was the sound sources. For receivers, I'm going to use rather simple receiver modeling in this demo. In demo number 2, we'll be demoing some more advanced receiver modeling. So here I'm just going to place 5 mono receivers at random locations in the room, like so. Okay, next aspect for setting up a simulation is to define surface materials. So with the SDK comes a very large database of materials. And this again is also continuously growing. People also have the ability to import their own materials. And we see some different categories of materials here. For example, a lot of porous materials and perforated panels. And we can, for example, take a deeper look into the category of porous materials. And then we see here, I'm printing the first 10 materials. We see their names, description, the absorption coefficients of each material. I can also analyze just a single material in more detail and, for example, plot the absorption coefficient and the complex reflection coefficient of this material. Okay, so this was the material database. Now I'm going to assign some materials in this meeting room. So I'll pull in here some different categories of materials into these variables, and then I'm going to randomly pick a material out of each of these categories and apply them on the different layers in the 3D model. So I'm just defining a function here to do this, and then actually call the function here and call a Sabine reverberation time estimation, so we can see roughly what ballpark of reverberation we can estimate with this material assignment. So with this randomly assigned material, Sabine is saying it's a reverberation time ranging from 0.4 to 0.25. And I can refit, and then we get some different reverberation characteristics. And I can do this again, and again, and again. And I'll just work with this material assignment here moving forward. Okay, so now we have assigned some random materials. We've placed sources and receivers into the room, so we are ready to run a simulation. So I'm going to show you how we set up a simulation, also how we can do some validation to see that everything is as it should be. So I'm deliberately going to place a receiver outside the model, and then I'm going to create a simulation object where I input all these settings that I've been defining, the room model, the crossover frequency between wave-based and geometrical acoustics. I'm saying it's a hybrid simulation. It could be just a wave-based or just a geometrical acoustics, but I'm doing a hybrid. Here I'm telling it how long of an impulse response we want to simulate. I want to simulate 25 decibels of energy decay in the room. So I don't know exactly how long that's going to be. That depends on the material and the acoustics of the room. I could also just set an IR length of 0.5 seconds or something, but this is a bit more efficient. Put in the receivers and sources and materials. So this is my simulation. And then I can call this validate function here and display the results, and it will complain. It'll tell me, there is an invalid receiver which is outside the model. So I can again visualize this simulation setup, and what we will see here indeed is that this receiver is outside the model. And then I can programmatically remove any invalid receivers, and now it's telling me the simulation setup is valid. So let's estimate how long this simulation is going to take. It's telling me that it takes about 0.009 hours, so it's a very quick simulation, 1 or 2 minutes or something like that. And because we have several different sound sources in the simulation, that actually under the hood many simulations will be running in parallel, so the wall clock time won't be affected, and this is the beauty of running it in the cloud. And then there is a cost estimate relating to how many compute tokens are needed to run the simulation. I'll come back to the pricing model of the SDK later. So let's just fire off this simulation. Now a machine is spinning up in the cloud, taking all this data and all this setup that we have defined, spinning up a machine in the cloud, or actually several machines, because we have several simulations actually running in parallel, putting all the data into the different GPUs, setting things up and running it. We can display the progress here, so this will kind of update every couple of seconds, and we see that the simulation is now running. So we see some kind of different components of the simulation. We have a GA simulation and a DG simulation, which is what the wave-based simulation is for the different sound sources that are running. And this will just take a couple of more seconds. So now I would suspect that most of the simulations are done, and it's mostly doing some hybridization to kind of combine different GA and DG results into a single coherent impulse response for each source receiver combo. So let's just wait a few more seconds. And now the simulation is done. Okay, so we can move on to analyzing the results. So I will going to result post-processing. I'm going to fetch the results here and store them in an object, and I can, for example, pull out one particular impulse response, like so, for a given source and receiver. We can plot the impulse response, and it looks something like this. we can plot the frequency response. So here at the lower frequencies up to, I think it was 700 Hertz, I said, is a wave-based simulation. So this is kind of accurately simulated modal behavior of this small room, and then the high frequencies are simulated with geometrical acoustics. We can get some different acoustic parameters of this particular impulse response, and here I, for example, just plot the early decay time. Okay, then I can convolve this impulse response with an anechoic sound signal to create sort of as if there was this is a speech recording, as if this person was speaking in this room in this position and the listener was at the receiver position. And then we can plot the resulting sound signal. So this is the speech recording in that room. We can plot the frequency response as well of this, and we can play it. So this is the anechoic sound, just the speech recording, some Icelandic speech.
Ja, og svo aðaldagurinn, svona, eftir hvernig lítum að. Já, einmitt. Já, ég var mjög ánægður með.
And then we can play the resulting convolved speech in the space.
Ja, og svo aðaldagurinn, svona, eftir hvernig lítum að. Já, einmitt. Já, ég var mjög ánægður með hennar fundan á hann.
Okay. So now we've gone through a single simulation where we did all the setup and ran the simulation, got back the results, post-processed the results. Now let me show you how we would do this for bulk setup, where we would want to simulate 1,000 rooms instead of just one room. And this is kind of where the beauty of the SDK really comes through, that this is very straightforward to do in a programmatic interface. So first thing, I'm going to be working with all the meeting rooms. So I already have pulled all the meeting rooms into this variable here, meeting rooms. So I'm now going to make a loop which loops through all of them and randomly assigns different materials from these categories as we did before, just in a loop now, as opposed to just doing it for one room. Now I've assigned materials for all rooms. This is the Sabine estimate of all different rooms, and let's say I wanted a bit more reverberant spaces than what we had here. So I'm going to take all rooms that fall out of this range here, 0.3 to 0.7, and I'm going to refit them with some other materials so I get results in this range. I do that here, and then we plot the Sabine again, and then we see a distribution like this. So now I've defined materials of 1,000 meeting rooms which have roughly estimated, Sabine estimated real times in this range here. Then basically I do exactly what I did before. I apply material, I've already applied the materials, but I've add sources, I add noise sources, speech sources, I add receivers in random locations. I create the simulation for every room. I just do exactly as I did before, but just in a for loop of looping through 1,000 rooms, as opposed to doing it just for one room like I did before. Just takes a couple of seconds, and this way I've set up not one simulation, but several thousands of simulations, because it's 1,000 rooms and several sources in each room. And it's creating these simulations on the server. So here we go. Now we have defined simulations for all these different rooms with different number of sources and receivers. We set a crossover frequency at 1500 Hertz, so going a bit higher in frequency here if we were for a data generation project where we wanted pretty accurate low mid-frequency results and some estimated IR length. And I'm not going to start this job, going to spin up thousands of GPUs, but I'm just going to show you here how we can estimate the compute time of this big bulk job, just by calling this estimate function, and it estimates the entire project. And it's telling me it takes around 6 hours for me to run. Each simulation is, as you can see, just taking less than 0.1 hour, but in my particular case, my organization has a concurrency allowance of 50 simulations at a time. So organizations can kind of buy into different levels of concurrencies. So you can have 50 simulations simultaneous, 100, 200, 400, whatever. And this then kind of decreases the total wall clock time. So here it's running 50 simulations at a time. And it's taking around 6 hours to run then the whole several thousands of simulations. And the compute cost for the whole bulk job is illustrated here. The compute cost will very much depend on how high in frequency we go with the wave engine. So here we chose to go sort of decently high, considering it's a bulk job. So the compute cost is then measured in 1,800 tokens, which I'll come back to later. This was it for demo number 1. Here we have shown how we create a simulation in the SDK and also how we create a synthetic audio data generation project. Okay, demo number 2, modeling a smart speaker with a microphone array using the SDK to model this kind of device in different acoustic conditions. And as mentioned in the presentation, we've developed some very elaborate methods to model multi-channel devices, to include the effects of the geometry and so on of the device. What we do here is we have an approach where we mix what's called device-related transfer functions, which is sort of similar to head-related transfer functions. It's a characterization of the device in free field, and then we mix that with very high-order ambisonics output from the room simulation to get the rendered microphone signals of this particular device. And in this demo, it's a Jupyter Notebook as before, so some pictures and comments and then the code itself. What we will do is we will import a first device, kind of a fake smart speaker that we have made here, run a simulation with that device in the room, and then get results out. What we're getting out then is the device-specific room impulse responses. And then we will show how we can, in post-processing, switch out this device for another device and get the device-specific room impulse responses for this device. And then we will do some post-processing of the device-specific room impulse responses just to kind of illustrate that this is doable. So, like before, we start with just importing some modules and then initializing the SDK and creating a project, which is like so. Then we're going to create a room model. Here we'll just use a very simple shoebox room, but obviously this could be a more complicated model if we want it. So we'll create a shoebox room with our geometry generator function, and we'll apply some random materials on the surfaces of this shoebox, and then work with this room model further. Okay, then going into the device modeling part itself. So here we have made kind of a fake smart speaker, for example, which has a sphere shape. It's a rigid sphere, and it has 12 microphones on it here in the horizontal plane. And we have taken this device and we have simulated it in free field conditions using the SDK to do that, to get the device-related transfer functions for all different incidence angles for all the different mics. This is stored in a standardized SOFA file format, and we can truncate at very high spatial orders to kind of capture this very precisely. So we have 16th order device-related transfer function dataset here for this device, which we work with. And then I'm just going to import this device into the SDK, so we can import SOFA files essentially. It can be a device or it can be head-related transfer functions also. And just for fun, I'm going to show you some device-related transfer, some frequency responses for different microphones of this device. And we see here for this particular incidence angle that at low frequencies the device has very little effect, but as the frequency goes up, then some microphones will be amplified. We also see some wiggles due to some interference of the rigid body of the device. And some frequencies, these are microphones who are kind of behind the device relative to the source position, they will be attenuated. And we could then switch to some different incidence angle, and then we will see basically that we've flipped which mics are attenuated and which mics are amplified. So this is device-related transfer function similar to head-related transfer functions. I'm then going to define a simulation where I kind of do as before, I'm telling it what type of simulation it is, but applying just a single omnidirectional sound source in the room. But what's different here is that I don't use a mono receiver as we did in demo number 1, but instead what we call here a device receiver, which is a SOFA file receiver. And we can set here how high of an ambisonics order we use in the rendering of this device and how high of an ambisonics order the spatial room impulse responses out of the simulation will be. And I'm going to choose very high order ambisonics, 16th order. And because I'm defining a rather small room, it was like an Etsy style room, then we can actually run this fully wave-based and it doesn't take too long. So I'm running it up to 8 kilohertz, just the wave-based simulation with this device in very high order ambisonics post-processing. I define this simulation setup here, and then we can evaluate how long it's going to take. And it tells me it takes around 22 hours to run on a single GPU. We could then have a setting where we say, let's split it on 8 GPUs, and then it will take roughly 1/8 of this time. Okay, I could also just have this be a hybrid simulation if I'm in a bit more of a rush. Hybrid, something like this. And then just going up to 2K, for example, with a wave engine. And then it'll take much shorter to run. Okay, but for the sake of demo purposes, I've already run the simulation here, so we don't have to wait for that. I ran the full wave-based simulation up to 8 kilohertz. So I'm not going to start and query the progress of the simulation, but instead I'm just going to pull in simulation results from the simulation I ran just before. And I pull in the results here, and then I plot some device-specific room impulse responses for a few select microphones in a particular time window. And this is kind of where the first direct sound and first reflections of this device is coming. And we can see, that some mics have kind of high amplitude. These are probably the mics that are facing the source, whereas other mics have lower amplitude because they are on the backside of the device. So here we have managed to run a simulation, very high fidelity room acoustic simulation, and captured the device and the impact of the device in the room, gotten the device specific room impulse responses. Okay, now I'm going to introduce a new device. Let's say we've done some iteration on our device design and we've decided, this device actually needs more microphones to kind of do what we want it to do. So I've created a data set of a new DRTF data set with this device here, which is the same rigid body but more microphones distributed around, a total of 28 microphones. So I can just import this one as well into the simulation. And I don't really need, into the SDK, sorry. I don't need to rerun the room simulation because I already have the 16th order spatial IRs from before for the room. So I can just kind of switch out the previous receiver device and introduce this new device instead with this function here. And now it's kind of rendering this particular device. And we can plot again the results. For some different mics. It's a device that has more mics now, and so overall the characteristics look similar as one would expect, but of course there are some nuanced differences, and of course there are just more microphone signals on this new device as well. So that's a way to show that you can, in post-processing, be switching out the receivers. You can change the orientation of the receiver in post-processing and don't have to rerun the simulation. Okay, and then one could use this to do some sort of post-processing, whatever one would think is relevant for assessing the performance of this device, whether it's some downstream tasks like doing automatic speech recognition or things like that, or more kind of evaluation of the performance of the mic array itself. And just for fun, we show here an example where we do some simple beamforming exercises on the two devices. So let me show you. This is the room that we ran the simulation for. So we have a sound source here and a receiver here. And we're going to do some beamforming to kind of ask the microphone array to assess the sort of direction of where sound is coming from. And the 0 degree azimuth is along the x-axis, so the true sort of azimuth angle is around minus 105 degrees, something like that. And first we can do beamforming on just the spatial impulse response, which had a lot of microphones because we needed to go to 16th order ambisonic, so it's around 400 receivers that are used to create that spatial IR. And if we run the beamforming on this for a particular frequency, then we see that this very large microarray is pretty good at identifying where the sound is coming from for this frequency. We can run it for a different frequency. And then we see some kind of prominent early reflections in the simulation results as well, but also the direct sound. And yet another frequency, and then we see kind of more, for example, a floor reflection here, which seems quite prominent. This is just, an example of what can be done with these kinds of results. This was the high order mic array, but now let's kind of use the rendered signals where we use a smaller microarray of either 12 or 28 microphones and do the beamforming again. And then we see that this is a much coarser estimate of where sound is coming from. This is for the 28 mics if we compare this to the top figure here. And if we use the 12 microphones, we get sort of an even coarser estimate here. So by adding more microphones, we see that it's doing a better performance of the beamforming compared to the 12 microphones. So this was a quick illustration of how you can do virtual prototyping of audio devices in the Treble SDK. Okay, now the last demo of today, showing how we can integrate the Treble SDK into a third-party solution and do parametric studies with the SDK. And in particular, we're going to integrate into Rhino and Grasshopper. So Rhino is here on the left. This is a powerful 3D modeling tool or CAD tool. And Grasshopper here is on the right, which is a sort of plugin into Rhino, which allows for kind of visual programming, so kind of making some visual programming scripts that can interact with a 3D model in a sort of rather seamless way. And what we are going to do in particular is we're going to investigate this open plan office here, which happens to be Treble's offices, and we're going to analyze the impact that the height of these partitions here that are between the desks have on the acoustics of the room. And we're going to do this programmatically through the SDK. So the 3D model is linked to Grasshopper. Grasshopper calls the SDK and runs some simulations and pulls back results, which we can view here in Grasshopper. So what we did, we obviously made the 3D model, and then we sort of picked out these surfaces here and say that these are kind of the parameters of interest that we want to play around with. And we've set some settings. We're saying that the height of these partitions range from 0.1 to 0.9 meters, and in a step, kind of 4 different steps. So we will study, you can see here as I step through the different variations, kind of different heights of this partition. This information is then fed into a piece of code block that we've made, which sort of interacts with the Treble SDK. So it takes this input information, it takes some settings of the simulations, it takes obviously the 3D room model. So here, if I preview here, and this is the room model that is fed in, and then the partitions are also fed in, and then some settings of the simulation. So in here is kind of a piece of Python code that talks with the SDK, and we intend to make this open source, this kind of Grasshopper integration, or an example of how the SDK can be integrated into Grasshopper. Now, so I'm going to insert a source and receiver. So we have a source over here and a receiver over here. And then we're going to analyze the sound pressure level at this position from the source here for these different partition heights. I'm going to put the transition frequency not too high so it doesn't take too long here in this little demo and simulate a rather short impulse response. But let's just fire it off. So when I connect these two things here, the simulations will start and sort of the code will start interacting with the SDK. So I will plug the source here and receiver here. And now this object here is sort of pinging the status every 5 seconds and displaying it here on the screen. And what we see here is now that these 5 room models that we've kind of parametrically made have been uploaded into the SDK. They are now being processed, some meshing and so on taking place. And then we will see the simulations start running. And once they're done, we will get back the results, some different acoustic parameters. And in particular, we want to view the sound pressure level for these different partition heights. So now the upload has been successful. Simulations have been set up, and it's estimating that it takes around a minute to run these different simulations. They're now starting, and yeah, we will have to wait around a minute or so. While we wait, I'm going to start looking into some of these benchmark examples that I'm going to show here after the demos, because the first benchmark is actually very relevant for this kind of scenario where we're analyzing acoustics in a sort of not very big room with some objects in the room, so a lot of acoustic diffraction and kind of complex acoustic phenomena happening in this space. So the first benchmark, sorry, it's a bit up here, is actually diffraction around the screen, which is what we're interested in modeling here. So this is a measurement scenario from a database called the Benchmark for Room Acoustic Simulations, which we have been very fortunate to get to work with to benchmark our simulation algorithms. And here we have a sound source that emits some sound that kind of bends around this obstacle, and then we have a receiver or microphone on the other end. And what we see here is that if we run a wave-based simulation for this kind of scenario, for especially the sort of low to mid frequencies where you have a lot of diffraction, sound bending around this obstacle, then we can model this quite precisely using Treble, using a wave-based simulation. So we see the frequency response is captured pretty well. But if you use a geometrical acoustics simulation, in this particular case we used an open source tool called Raven, which is an academic room acoustic simulation tool, which does actually include some approximate diffraction modeling in GA. We still see that that tool is not able to capture the frequency response or the true kind of way of sound bending around obstacle like this. So using a wave simulation or a wave hybrid approach where the low frequencies are modeled wave-based, then you can trust to get good estimations in this kind of scenario, like open plan offices, which are of course often very tricky to simulate. Okay, simulations are done now. So here we just see the result. So for these different partitions heights, we're printing just the sound pressure level, and we see when the partitions are quite low, it's around 98 decibels. But if we have higher partitions, then we manage to reduce the sound pressure level by some 5 dBs, and that's notable. And of course, we could analyze further acoustic parameters like the open plan office parameters, privacy distance and distraction distance and things like that. But this was just to illustrate the point that we could connect the SDK and a 3D model through Rhino and Grasshopper. So that was demo number 3. Now the demos are done. We'll go back to the presentation. Okay, coming back to the benchmarks, we've already looked at the first benchmark study, which was the diffraction around the screen. Second, somewhat similar study, also in a kind of semi-anechoic chamber where we have sound emitted from a loudspeaker, hits a complex geometric surface and is reflected back. And we want to model this as precisely as possible. Again, coming from the benchmark of room acoustic simulations, the measurement data. If we first turn our attention here to the right, this is from the paper of the authors of this database. And then we see the measured frequency response here in black between the source and the receiver. And then these are different simulation tools available in 2019, I believe, all geometrical acoustics based, trying to model this scenario. Because they don't model diffraction and interference and things like that and complex geometries very well, then they are not able to model this kind of scenario, complex geometries and complex acoustics. However, if you do a wave-based simulation here and in the low mid-frequency range, then with treble simulation, then you will match this very well. Third scenario, which is again similar, instead of having a thin screen, we now have a thick barrier, and results as before. Wave simulation captures this frequency response very well, whereas geometrical acoustics, even trying to have some diffraction modeling included, does not really capture this. Okay, now going from a sort of isolated acoustic phenomena study to a full room study. This here is a small room study, then we also have one in a bigger room, where Treble conducted measurements in this room here, where we placed directional sound source into the room, recorded both mono and binaural room impulse responses in the room, to test and validate both the room modeling and the receiver modeling and source modeling capabilities of Treble, which were all relevant in the demos showing before. So here we have the setup. We have different source positions throughout, as well as receiver positions, either mono or binaural recordings. The receiver modeling, I talked a bit about this earlier. So we have a data set of what we call the device-related transfer function, or in this case a head-related transfer function of the KEMAR mannequin, which is fed in post-processing after the acoustic simulation. And in the acoustic simulation, we have a sort of a virtual microphone array at the receiver position to model or to simulate a spatial IR with very high order ambisonics. And then in post-processing, we mix the data set of the device and the spatial IR to get as if the device were in this room. And this is beneficial because then afterwards we can change the device, change the orientation of the device, and so on. So let's first look at some mono results. This is a room impulse response simulated and measured. And as we can see, there is a very good match between the two. These prominent early reflections are quite well captured in the simulation. Here we see a frequency response, so the low frequency modal behavior of this space is captured very well, and also the sort of high frequency trend, including the directionality of the loudspeaker and so on. This was a full wave-based simulation up to 8 kilohertz that we did. These are energy decay curves at different frequencies. They match very well. Material properties in this room were quite well known, so we had measured the impedance of these stone wool absorbers that were in the room. And room acoustic parameters matching very well. Here's the T20 reverb time. Note, for example, this interesting increase of mid-frequencies probably due to flutter echoes, and the early decay time as well for some different, for arbitrarily chosen source-receiver combo. And then the binaural results, where we mix the HRTF and the very high order, 16th order ambisonic IR to render out the ear signals as if that mannequin had been in the simulation room. And we see also a very good match between measurements and simulations. You see the difference between the two ears. So clearly the right ear here is facing the source. So it's much louder amplitude here compared to here, and so on. We can also listen. So we have a couple of audio demos here. First some speech and then some music. So what I'm going to play is the anechoic sound that went in, and then convolved with the measured room impulse response, and then the measured binaural room impulse response, and then the simulated binaural room impulse response. And this is more convincing when listening in headphones, because then you also hear this kind of where the sound is coming from. So let's first play the anechoic speech recording. Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity. Okay, and then convolved with the measured binaural impulse response.
Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity.
And now with the simulated scenario.
Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity.
So in my totally unbiased opinion, I think they match quite well. There's maybe some slight kind of high frequency reverberation in the simulation, which is more prominent than in the measurement, but overall I think this is a very good match, and the sort of spatial sound to me sounds very convincing. Okay, music, signal, hear the anechoic sound. In the measurement, so different source receiver combo. Okay, and now a large room study, where this is coming from the benchmark from Room Acoustic Simulations database, big auditorium which we simulate in a hybrid approach, not a wave-based only like we did in a small room. And just quickly, some results here, some different acoustic parameters where we compare treble and the measured results. Clarity and definition are really spot on here. The center time is also quite close, maybe here in the lowest frequencies, and also for the early decay time there is some difference, which is most likely due to uncertainty in the material properties, as the authors of the database acknowledge that this is quite uncertain in this range. But overall, a very good match. We ran the wave-based simulation up to, I think, 500 Hertz, something in this mid-frequency range here. So, showing that we can do both large and small rooms very well. Okay, finally, a couple of examples where we're not really comparing measurements and simulations, but more showing some interesting academic research that we've come across, which analyzes the impact of using more high-quality synthetic audio data on various machine learning algorithm performance. Two studies I want to highlight. The first one here, coming out of DTU, where they trained a neural network to do blind room estimation. So you feed it an impulse response and it tells you back what is the acoustic properties of this room I'm in and what is the size of the room. And they trained two machine learning models to do this task. One was trained on wave-based data, wave-based transfer functions. So it's fed wave-based transfer functions and told, okay, for this transfer function, the room is this size and has these absorption properties. And then the next transfer function has this size and these properties, and so on and so forth. And the network is trained to sort of learn a mapping from a transfer function to these output parameters. Then they did the same for another model, which was just trained with geometrical acoustics transfer functions, simulated transfer functions. And then they, by the way, this was just in shoebox rooms, so and just at sort of low frequencies. And then what they did after they had trained the two models is they feed them measured real transfer functions in a shoebox room where they know the size of the room and the absorption properties, and they asked the model to to spit out what is the size of the room and the absorption properties. And very interestingly, what they found was that the model trained on wave-based data performed much better than the one trained on geometrical acoustics data. This is maybe not a big surprise because a wave-based simulated room impulse response or transfer function is much closer to a real measured impulse response than a geometrical acoustics impulse response, especially at lower frequencies. What we're seeing here is a graph from the paper where they're comparing the error in absorption estimation for the two models for some different configurations of the room. And they note here that the absorption estimation error was twice as large with GA data over wave-based data. So it's kind of a good indication that you can expect better performance of machine learning in blind room estimations when using wave-based data to train your model. The second study I want to highlight comes out of the University of Maryland, where they did something very interesting. They created a data set in kind of pretty complex scenarios of apartments using a similar approach to what Treble is doing, but still somewhat different. They're using a finite difference wave-based engine, not a finite element engine. But other than that, sort of somewhat similar approach, maybe also a bit simpler sources and so on. But then they took this data and trained 3 types of audio machine learning algorithms on this kind of hybrid wave GA data and compared that to training it on GA-only data. And what they find is that in all cases, performance improves for automatic speech recognition, for speech enhancement, and for source separation. Very powerful results, and I encourage you to read this paper for further details. And there are more validation studies constantly trickling in at our website as well. Okay, here in the end, just a few words about what lies ahead. So even though the SDK is a very powerful tool as is, there's of course further development taking place. So here in the very near-term future, we expect to release more features relating to sound source modeling. For example, a new boundary velocity modeling approach, which is particularly good for low-frequency sound source modeling in wave simulations. Also the ability to import your own sound sources into the SDK. More advanced programmatic capabilities for generating and modifying rooms, such as populating rooms with furnishing and so on, moving that around and things like that. More seamless workflow for generating DRTF datasets or HRTF datasets, which you can then use for virtual prototyping use cases and data generation, kind of like we demoed before. Integrating with public speech and noise data sets to make the convolution step a bit more seamless and data generation a bit more seamless. Outputting not just room impulse responses in chosen points, but actually the whole sound field, either from wave-based or geometrical acoustics is coming, and transmission modeling between rooms and so on as well. So all of what I just highlighted here is actually on the sort of very near-term agenda. And then we have at least a couple of bit more longer-term research projects going on, which have shown promising early results, but which is real-time simulation, where you can in real time get room impulse responses, accurately simulated room impulse responses. Then you could use the SDK to power, for example, virtual reality experiences and so on. And the ability to model moving sound sources, if you want, for example, data sets of moving sound sources. This is being worked on as well. So that was a very quick overview of what lies ahead for the SDK, or at least some of what lies ahead. Regarding the pricing of the SDK, the pricing model is a combination of a fixed subscription fee. The amount itself varies depending on how many users an organization has, how big of a concurrency requirement they have, meaning how many simulations they want to be able to run in parallel. Basically those 2 parameters dictate the fixed fee. And then there is a token-based system. So typically organizations would buy a bundle of compute tokens, and that allows them to run X many simulations. How many simulations you can run with how many tokens, that depends a lot on how much of a high fidelity simulation you run. If you run a full bandwidth wave-based simulation, it's going to take longer time and cost more. But if you run a hybrid simulation, then it's more efficient and costs less tokens. So it sort of depends on the use case and the desires of the users. So, for example, a bundle of 10,000 tokens can result in thousands to millions of simulations, depending on simulation fidelity and sizes of simulations as well. The SDK will be free to try for anyone who's interested, and they will get free compute tokens while trying. So please contact us if you're interested in giving it a spin. There is a form on the website where you can sign up. We will be rolling it out in a bit of a controlled fashion here in the very beginning, because there is simply a lot of interest in this product, and we want to ensure that the first users have a good onboarding journey, and that we address any issues that might come up here in the very first few days and so on. So we ask people to sign up for a waiting list to get access to the SDK. some months down the road, or weeks or months, this will be a more automated process where you can get it right away. That was kind of it for today's presentation. It's been really exciting to present this to all of you, and we're very proud of this SDK product and hope that it will add value for our users. I know that quite a lot of people have been waiting for this for quite some time, so it'll be fun to see it in action. And now let's just move to questions and answers. Thank you. Okay. Hello everyone. Now we move over to the questions and answers part of this webinar. We've gotten some absolutely fantastic questions from you guys, and I'm excited to dive into them. So I'll just take them off one by one here. So the first question is, are we able to export geometries so that you could, for example, do some comparisons to other software? And yes, the answer is simply yes. You can export geometries from the SDK and then use them for your further processing. Okay, second question, should we make the presentations publicly available? Absolutely. So we're putting quite a lot of our stuff already on YouTube. We have a YouTube channel, so you will be able to find this there. Great question. Here comes a question from Joel. Is SketchUp still the only supported CAD program, or has this been expanded, for example, Blender or Unity? So in the SDK, you can upload generic 3D file formats, whether that's OBJ or DXF or 3DM. There's a variety of formats that are supported kind of off the bat. In the acoustic simulation suite, the graphic user interface tool, right now we have a plugin into SketchUp there, which sort of live links the web app and SketchUp, and soon we will be both releasing plugins to other 3D modeling tools for that product, and the ability to upload kind of generic file formats as well. Specifically regarding universal scene description, I think it's what it stands for. We haven't tried that one yet. It'll be very interesting to explore that one, and absolutely the kind of future path is to support a wide variety of 3D formats, and very interesting to integrate with VR engines or gaming engines like Unity. Okay, loudspeaker data ingested in the GLL format. I wish I could say yes, but GLL is a closed proprietary format which we cannot use. So what we support now is uploading from CLF format, which is common loudspeaker format, and then we are working with loudspeaker manufacturers these days to establish essentially a new Treble format, which allows the import of their loudspeaker data into Treble. So we are in active dialogue with many of the big loudspeaker manufacturers these days, and absolutely the goal is that you could simulate pretty much any loudspeaker in both the SDK and the simulation suite. So CLF right now, more coming soon. Is it possible to import a head model with microphones, positions at the ears to simulate individual HRIRs, etc.? Or only possible via SOFA? So right now what we support in the SDK is the SOFA import, that you can then have a HRTF dataset or DRTF dataset, and this way get the rendered signals at the ears. Well, I guess what's being referred to here is rather, instead of doing that, to insert the geometry of the receiver into the room model and have that be a part of the simulation. This will be supported soon when we improve a bit or add to the geometry processing capabilities, that you could add like a CAD model of a device or a person or whatever. There's sort of pros and cons to these two different approaches, the SOFA approach versus the geometry approach. The SOFA approach is attractive because then you don't have to rerun the room simulation if you have a new device or if you want to rotate the device. This other kind of inserting the geometry approach is attractive because it's maybe slightly more precise, because it takes into account the interaction. The kind of object has the impact, the impact that the person has on the acoustics of the room is more taken into account this way. And this will be supported down the road, but the SOFA approach is what's currently supported. Okay, nice comments from Joel here. Excited to use the SDK. I'm very happy to hear that. I have to say myself, I was just watching the whole presentation, and I think we've done a pretty Good job here, and this is a really exciting product. It's kind of a new and unique product in the world of acoustics and audio, this kind of SDK simulation engine. So I hope that you guys are excited to use it, as excited as we are about it. Here's a nice comment from Roy. He loves Treble so far. Thank you so much for that. So, sample rate of the auralization will be 44.1K, and the bit depth, yeah. So I think our current sample rate in the simulation suite is 32 kilohertz, because we simply simulate up to maximum 16 kilohertz. So you could then upsample this to go to 44.1. But you know, you wouldn't get much more data or information in your signal because the simulation is only valid up to 16 kilohertz. But this is an interesting comment. I think the resolution is 16-bit already. So this is kind of noted. I'll discuss it with the team. Thank you for this. How detailed can the source directivity be modeled? This is a great question, and requires a bit of a long answer. So we have two simulation engines. We have the geometrical acoustics engine and the wave-based engine. For now, we're just doing point sources. So things like surface sources, combination of point sources to make like a line array and things like that. We're working really hard on these things, but it's not supported yet. So we're talking about directional point sources. And then in geometrical acoustics, that's actually quite trivial to do. You simply scale the energy of the rays emitted from the source according to the directivity balloon of the source. Easy, easy. The wave-based part is a bit more nuanced. So what we do now is we sort of fit a model to the directivity balloon, and then we can excite the model with this fitted directivity. The fitting is quite okay now for most intents and purposes, but we're absolutely working on making it even better as well. I hope that answered the question. It's a whole topic in itself, source directivity, and we're working really hard on that. Multi-room simulations, was there any kind of transmission loss? So I guess maybe this was covered a bit later in the presentation, that transmission loss is being worked on these days, and we expect to release it in Q1 of 2024. Does the calculation happen in the cloud or not? So short answer is yes. The calculation happens, the room simulation happens in the cloud, the sort of simulation of the room impulse response. Post-processing, things like convolution, calculating acoustic parameters, things like that, that happens locally, but the room simulation itself happens on the cloud. This is the standard offering. If people are interested in running the SDK, for example, on their own GPU farms, or their own servers, this is absolutely something we can discuss. Can you apply smoothing to the frequency response? Yes, it's maybe not a function that is a part of the SDK, but you could certainly use some standard Python functions to do something like this, for sure. Is it possible to simulate low frequency propagation outside from industrial sources? So I would say yes and no. The engine is very well suited for doing low frequency simulations. We do not yet, we're not yet supporting sort of, let's say, weather effects, wind and things like that. So that's sort of on the bit longer term roadmap, let's say. So if you have a sort of not a huge, like not a whole city style outdoor sound problem, but more like, yeah, like, you know, industrial plant and kind of the area around it, or a new building site or something like that, then you can actually model the low frequency propagation quite well with the wave engine, with the kind of asterisk that the weather effects are not taken into account. And we have a PhD or research project ongoing in collaboration with DTU, where we are researching ways to improve outdoor sound modeling and integrate that into Treble. Transmission loss, another question. I guess that's already been answered. That's coming very soon. Is there a way to get which way to get the output, only convolution. So what the output of the room simulation is the room impulse response. This can be a mono impulse response or a spatial impulse response where you can set the ambisonics order ranging from 1 to 16. You can get this directly. Then you can also mix an HRTF or a DRTF to get the rendered kind of device-specific or head-related room impulse responses. You can get this out as well. And if you then choose to convolve anechoic signals with the impulse responses, then you can obviously export that as well. Optimization on convolution. So we have not developed specific convolution algorithms here at Treble yet, so we're using, I would say, standard Python convolution algorithms for this, and this is documented in the documentation precisely which algorithm is used and so on. Tangi, outdoor sound propagation to the roadmap. I guess that's been kind of covered. We're working on it in collaboration with DTU. Actually have some very promising early results, so stay tuned for that one. Can materials created in the web version be imported into the SDK? This is a fantastic question. So as of now, and kind of actually a bit of a bigger question than just materials. So as of now, the SDK and the web tool are not connected. That's a bit of an internal discussion at Treble these days on whether these things should be kind of coupled to be one and the same, or whether we should have like a separate user interface built on top of the SDK. And I just have to be transparent that the jury is still a bit out on that. So right now these things are separate, and yeah, we're making up our minds on how we tackle that. But you can absolutely import materials into the SDK and into the material database that you have for your SDK user. Able to export room impulse responses, multi-channel. I guess I've already answered that. Absolutely. How does oralization mix with Unreal Engine now and in the future? Right. So I touched a little bit upon kind of getting the geometry from a thing like Unreal or Unity into the SDK. We haven't specifically tried that, but generic 3D room models are supported. So I could imagine that these two things should align very well. And this is actually just a great opportunity for kind of the community could build, or someone could take it up on him or herself to build a little plugin into Unity that or Unreal that sort of links Unreal with the Treble SDK. We might also do it here ourselves. And then oralizations. So as of now, the SDK is not a real-time simulation engine. So you could pre-compute or impulse responses in the room. You could do it on a grid across the room and do some interpolation to allow you to move around in the room afterwards, or just jump between static points and so on. But you would have to sort of pre-bake the acoustics in the cloud beforehand. Real-time simulations is something we are working on. We have some fantastic talent here doing very interesting research on utilizing machine learning methods to enable real-time simulations of rooms. It's, again, promising early results, but it's being worked on. How does the simulation scale with a number of sources and number of receivers? It scales. The compute effort scales linearly with number of sources. So if you have one simulation with 5 sources and then the same simulation but with 10 sources, then it takes twice as much compute effort. But the user doesn't really feel this, because what happens under the hood, or in the cloud more specifically, is that 10 machines would be spun up instead of 5. And the time the user feels it takes to run the simulation would be exactly the same, whether it's 5 or 10 or 500 sources. Receivers are more or less for free. There's some data processing that happens, obviously if you have 10 16th order receivers, then there's quite a lot of data that comes out of that, and some post-processing that takes time and so on. But for the simulation itself, receivers are really just kind of recording where in space we record the output of the sound field. What's the best way to browse the documentation of the SDK? This was actually something I was going to include in my presentation, but kind of last minute simply forgot. So if you go to docs.treble.tech, then you will see our documentation. There are kind of 4 sites there. Or 4, was it 3? At least there is kind of a user guide for the simulation suite, the web-based tool. There is a user guide for the SDK, which shows both tutorials, for example, the notebooks that I was showing here earlier, and kind of function reference. So for every function that's in the SDK has a description and the inputs and outputs and things like that. Then there's also this validation site there, which shows all kinds of benchmarks that we have done. Here is Lucas, who asks, well, first says congratulations. Thank you so much, Lucas. Startup idea for technology that would nicely integrate with Treble. Would you support my project? Well, let's talk about it, Lucas. It sounds interesting. Absolutely. And here, the last question. What parameters are needed to characterize your own surface? So you can import materials in a couple of different ways. You can either specify the random incidence absorption coefficients, which is sort of the traditional way of characterizing surface materials, where you put, octave band absorption coefficients. And then we have a method that takes that and converts that into surface impedance. So kind of adds the phase information to the material, and it sort of tries to do the best guess it can do given the absorption characteristics. This is maybe not the most precise way, but it's still better than nothing if all you have is absorption coefficients. And you could also import impedance directly, either in octave band or 1/3 octave band resolution. A bit further down the road, we have been planning and working on sort of what might be called the material generator, where you sort of more specify the build-up and properties of your material, and then we use analytic models to compute the impedance of this construction. So that's on the roadmap. Okay, I think that was it for the questions, and I think we're quite a bit over time anyway, so maybe that's just perfect. These were absolutely great questions. You guys are always welcome to reach out to either me directly or to us here at Treble. We have a live chat on our website, so if you write in there, there's not a bot that answers you, but actually a human being that answers you. So if you have any questions or comments, feel free to reach out to us there. Obviously, also you can send us an email. If you're interested in trying the SDK, then please sign up to the waiting list. We wish we could roll it out to everyone from day one, but that's simply not possible. But we will do our best to sort of go through the list as soon as we can. So please just sign up there. If you're just interested in trying it, no commitment or anything with signing up to a free trial, and let's take it from there. So thank you so much for today. It's been a pleasure. And now I think we at Treble are going to pop open a couple of beers and celebrate a bit the launch. Goodbye.